mainly because we just now started the recording. So this lesson is about testing. It's the most important aspect of a smart contract is to make sure that it works as supposed to. It can be slower or faster. It can be cheaper or more expensive to run, but it cannot fail. It cannot release money or assets to someone that is not supposed to. So correctness is the most important, the crucial aspect of a smart contract. And testing is a big chunk of our efforts to guarantee correctness. So we're going to do two examples today. We're going to start with a simple, easy to test example, and then we're going to create a real, like in the real world assets, a real world example of a smart contract that is used in the wild, but if not implemented correctly, it can release assets to someone it's not supposed to. And we're going to find those that exploit with our tests. So let's start with the first validator. This one is pretty simple. So we're not going to wait too much time in the actual process of writing the validator, because we already wrote like 8 validators already. So you know the drill by now. But let's see, our first validator needs to check two things. Let's say, check. First, the redeemer must be less or equal to 0.
Robertino,
Yes.
you are not sharing your screen?
No.
Sorry.
Sorry, guys. Thank you so much, Karina. Sure. There you go. We're good now, right?
Not yet.
Not yet. It says presenting, but I can stop and do it again. Share screen. Sure. Okay, now looks good.
Yes, now.
Awesome.
It's okay.
So, what do I say? We want to check two things. First, that the redeemer must be negative or 0. And then we want to check that a certain deadline saved in the datum passed. So if both return true, we authorize the transaction. Else, we don't. We reject. So let's see. We start, as always, with the validator keyword. This validator block. We have to define the function that we can name this however we want. I'm going to name it negative redeemer timed, because we need a negative redeemer and it's timed because we have to provide the deadline. So this is a spending validator, not a minting validator like the one we saw in the last lesson. So as you recall, we have to provide a datum. Even if we don't use it, we have to provide this like placeholder datum. In our case, let's see to do. So let's import script context. In our case, we want to use it actually. We want to use it because we want to provide a deadline. And we could say, for example, we could say deadline POSIX time, and this will work. But what we're going to do to make the testing side more interesting, we're going to create a custom type custom datum that is going to hold this deadline. And we're going to provide the datum as custom datum. There you go. Okay, so let's try the first check. The first check, I think, is quite easy. So we want to know if the redeemer is less or equal to 0. Right now we're not using the redeemer; it's just empty. So we know that it's going to be a number because it has to be less or equal than 0. So let's change this redeemer. Let's remove the underscore to use it. Redeemer, and we can say it's of type integer. So this redeemer of type integer, and if we just wanted to check that, we can say redeemer is less or equal to 0, and we will be done. But we also want to check about the deadline. In this, with just this validator, independent of the date, is going to return. Is going to validate the transaction if the redeemer is negative, and is going to reject it if it's positive. So we want to we want to check to get the time, and we know, because we already did it in the besting validator, that we can get the interval of the transaction using that it's inside the context. So let's start doing this like the right way. Let's start with checking that we are using the validator the correct way. So when the context, where I'm not using context, so let me remove this underscore. There you go. When context purpose is, and now we say spend, and we have the reference of the output we are spending, but we don't really need. We just need to know that we are expending an output of this validator, and spend, and then here in any other case we just return false. So if we are minting or doing like managing all other options that you could do with validator, we're just ignoring. So when we are spending, we need to check the deadline. So we already did this with the besting validator. So we could actually extract the logic and import it from a library or something like that. But we're going to like redo it super quickly right now. So we have the context, and inside the context we have the transaction, as you recall. So we can pattern match to extract the lower bound of the validity range of the transaction by using and we pattern match. We know that transaction has a single constructor that is also called transaction, and transaction inside has this bunch of stuff. So we are interested in the validity range. Just in case, let me serve. just to make sure that you know where I get this, all I need to do is say transaction. And let me zoom a bit. There you go. And inside transaction, we have all this, and inside there, we have this, the validity range, which is of type validity range. And we already knew the validity range is actually just a synonym for interval of POSIX time. And we already know that interval val we already know that interval has a single interval constructor that has a lower bound and an upper bound. So we just have to drill down to get that value that we need. So we pattern match transaction to extract validity range. And we could extract other stuff, but we are not interested in anything else that is not the time. So we just use the spread operator to ignore it. But inside validity range, we know that it's an interval, so we can also pattern match again, interval, to extract the lower bound that we just saw right here. And now that we have the actual interval, then we have to import, oh, sorry. We have to import span. And we have to import transaction and the interval. Yes, it's what is it? So one field in a context where there should be two. Yes. So as you can see right here, interval has lower bound and upper bound, but I'm not interested in upper bound, so I can just ignore it again. And there you go. Like this works. Let me write to look here to show you that. No, let's write. I found this current expression not bound to a variable. Yes, so we created the let. We created this bounded lower bounds expression, but we are not using it anywhere. So the compiler is angry at us. So let's use it. So we have the lower bound, and we already did this. So we can just do it once more. We have to check that the deadline, the deadline is less or equal than the earliest time of the transaction. The earliest time is the lower bound of the transaction. So let's say, let's create this let is after deadline. And lower bound, interval bound, we have lower bound is of type interval bound, and we have this bound type that is of type interval bound type that can be either negative infinity, finite, or positive infinity. We are interested specifically in finite because negative infinity should fail, because if it's negative infinity, you could be sending the transaction before the deadline, and it cannot be positive infinity because it's a lower bound. So let's see. So we can pattern match. We can say when lower bound, and this is bound type. Bound type is when it's finite. We'll see what we're going to do, and in every other case, it's false. We have to import finite. So we have the same error again. We are creating this but not using it anywhere. We're going to use it right now. So what happens if the lower bound is finite? We get here the transaction earliest time. We have, in fact, the earliest time that anyone can send this transaction to be approved. And if that is bigger than the deadline, so now we can say datum dot deadline. If the datum is smaller or equal than the transaction earliest time, then that means that the transaction is actually being performed, being submitted after the deadline, so we can actually approve the transaction. So now all we need to do to finish our checks, we can just do validator checks, validator final checks, and we can say we are going to validate this transaction only if the redeemer is less or equal than 0 and is after the deadline. And oh, this should be no there. Let me see. There's something wrong here. When is finite? Let's see, where's the error? I found this card expression. Yes, but not super useful. Validity range is of type interval, lower bound. I think that's fine when lower bound type is finite, else false. I might be missing something, but I cannot see where.
I think this is because at the end of the function, we have a statement of comparing the redeeming with 0, and we already have that in
Yes.
in the when. Okay.
You're right. Thank you so much. I was completely oblivious to that end part that I Perfect. Thank you so much. Thank you so much. So yeah, the validator was right, but we had some extra bits from the explanation. Awesome. So that's it. We have our validator and we could start using it, but we are not sure if it actually works as expected. So let's test it out. We have, as I'm sure you recall, various ways of testing. But we're going to start with unit testing and then move to property testing. To test these validators, we have to, because they are pure, these validators are pure, we have to provide everything the function needs to actually like check that to do. So the validator can perform its the check, can return either true or false. We have to provide these 3 parameters. The context, the script context, is the most involved and the longest one. So we're going to try to do that quickly, but it's important to notice that we in this case, the script context, we only care about the lower bound. So we're going to just use default values for everything else, because that we are checking the lower bound. So let's create a function. We have to change, we're going to vary the earliest time of the transaction to check before and after and stuff like that. So we're going to use it as parameter. Let's create a function called create context. And this function is going to take the transaction earliest time. This is a POSIX time, and it's going to return a script context. So the script context has transaction and purpose. Purpose is pretty straightforward, but transaction is like quite big. We're not going to actually define all these values, but we have to at least instantiate them. So let's see. Let's start with our inputs. Let's start with the interval, which is the thing that we care about. So let transaction interval is of type interval of POSIX time. And this transaction interval, we use the interval constructor that takes lower bound and upper bound. But let's do this. Let's do the lower bound first. So lower bound is an interval bound. We just saw that interval bound. And the interval bound, if we see right here, lower bound has a bound type and also has like this property that says if the type is inclusive or exclusive. So we can say bound type is we care about being finite, as we saw. Like we are creating right now the transaction itself. So we want one that could potentially pass the check. So we say finite, and we provide the parameter transaction earliest time as the value of finite. So then when we create the tests, we can change this parameter and we can check both sides of the time range. So we have the bound type, and if is inclusive was a Boolean, so true. And there you go. We have our interval bound. Let's save. Create context. Oh, let's save. But we still need the upper bound. Upper bound is also actually, if you just copy this. So we have the interval bounds. It's inclusive, yeah, but we cannot have an interval that is a zeroth, like that contains zero time, because the lower and upper needs to have some difference in range. And we don't really care about the upper bounds, because like we don't check for it, we don't use it, we just care about the lower bound in this case. So we're going to say POSI, we're going to say positive infinity. And this we have to provide the script context. Let's see, maybe I can do to do. There you go. Eventually, we have to return a script context because I already said so in the type. But in the meantime, we have a type we have an interval that could potentially pass our tests. Okay, now we can create the transaction. Let's transaction of type transaction equals to, as you recall, transaction has a single constructor. Transaction, and we have a bunch of stuff here. So we have inputs that I can use an empty list. I mean, this shouldn't ever happen in the real blockchain, because you always need to consume an input to actually pay for the fees of the transaction. But in this case, we're just testing the smart contract, not the blockchain itself. We're testing the smart contract, and the smart contract, in no points, it checks for the inputs nor the outputs. So we can just avoid providing those. We'll see that in other cases, in the next example after this one, we actually need them, so we have to produce them. But in this case, we can just ignore this. We can reference input, output, reference inputs. It's also an empty list. Output is also an empty list. The fee is of type value, so we have to create 0, I believe, or maybe just, let's see if it gives me, oh, it will like keep failing. So let's move on and let's do all the fields before moving on. So mint, we need also a value, but in this case it's a minted value, so we want to use 0, but we have to convert this to mint. So to minted value, there you go. And now we want certificates, withdrawals, validity range, extra signature. So certificates, also a list. We have withdrawals, which is a dictionary. So we can say dictionary new. It's an empty dictionary. Validity range right after withdrawals. Validity range is the one that we just defined. Transaction interval. Then we have extra signature, redeemers, datums, ID. Extra signatories, an empty list. Redeemers is a dictionary as well. Dictionary new, was it? Yes. Datum, also a dictionary. New. And the ID of the transaction, in this case, is transaction ID. And if we see right here, it's just a hash of the transaction, Blake 2B256 hash of the transaction. So we can just fake that because we are not checking for the transaction ID, but we have to actually like construct it. So transaction ID with the hash of, and now I can just put anything here as a hash. So 1, 2, 3, 4. There you go. So we have all the fields of the transaction defined. And as we just saw before, the transaction is one of the values that we need for the script context. So I will have to import 0 and transaction value and 2-minute value and the dictionary. And transaction ID, we have to import all this. There you go. Finally, we still have to use this transaction. So let's use it. So we have to create, now we want to actually provide a script context. And this script context needs the transaction and the purpose that we check in the top. If we go to the validator, we check that we need to spend, and we need to like actually be running a spending validator, but we don't really care about the actual output ref that we're consuming. We just care that it's spending. So we have to create a spend. And here we cannot just like pass anything. We need a output reference, even if it's fake. So let's create that. Let's go here. Let input ref input out ref. And we need the output reference. Let's see. Output reference, transaction ID, and output index.
Robertino,
Yes.
uh,
We have a question?
no, it's only a comment. The screen with the code is not visible.
The screen with the
Code. I think for Anderson. but-
right. Right now they cannot see the code.
Anderson, could you see the script now?
Okay. I'm seeing a screen, but I don't see where Robertino is editing the code. I think it's a blank screen at the moment.
Okay, I will stop sharing and reshare again. Karina, you were able to see the code?
Yes,
Okay.
I able to see.
But
Okay,
maybe
so-
you can stop sharing and restart. Can't do harm.
Share screen. Let's see. So can you, Anderson, can you see now the code?
I think it's not yet. I think I'm seeing your profile at the moment. Maybe you can reshare it. Yes.
Yes. Awesome.
Now that's good. Yes. Thank you.
Awesome. Yeah, let me know, because I think you are recording, so you should be the one that sees everything always.
Okay.
Awesome. So just as a recap, we need a script context, and to provide a script context, we need the transaction and the purpose. So we painstakingly build everything needed in the transaction, just as default values, except for the thing that I really care about, that is the validity range. The validity range, we created on purpose at the very beginning to define the lower bound as a finite thing that we can provide as parameter to the create context function. So far so good. But now we need, for the spending constructor, we need where is it? There you go. An output reference. Output reference. and the output reference has a transaction ID that we can actually let TX ID, and we can just use this one just to be consistent, but not really an issue. We could just repeat the code. TX ID, transaction ID is output reference transaction ID show ID TX ID, and now the index, because like we need both the transaction ID and the output index to identify a reference. So output index, and we're going to use just 0. Like we're going to hard code both the transaction ID and the output index because we don't really care about. So now we can input out ref, and hopefully this shouldn't be there. Okay, we have to import output reference. Okay, fine. We have no errors, and we successfully created a full script context that then we can reuse again and again. So now it's time to write the tests. We want to check a couple of things. So if you see this as a grid, oh my God, I think I need to do this. Yeah. And if you see this as a grid, like the possible combinations of time and redeemer, and we can say, okay, in the x-axis we can put the deadline right here, for example. Deadline is like this, like the 0th redeemer indicates the deadline as well. So, and we can actually put here redeemer equal to 0. No, let's just put 0, and everybody understands that this is the 0. So we have like 2 parameters that the combination of them could be anywhere in this grid, right? So what we want to check is, I mean, if we run these checks, for example, let's see, we can, let's see if I can do small little circles. If we check right here, there you go. If we have the deadline and the time, we want the validator to return, like to validate the transaction if we are after the deadline and if the redeemer is 0. So this transaction with these parameters, no matter like which parameters are, should return true. Actually, we can have like this to say, okay, if it's 0, it should be true. And if it's any negative number as well, should be true. But then we also want the rest of the grid to return false. So if we create a transaction right here, we want it to be false. if we create the transaction right here, we want it to be false. Right here, we want it to be false. So we don't want to like actually, let's do it. It's ugly like this. So this is nicer. So this represents kind of all of the, and this one could be actually exactly like right here. This will be sort of like a proxy of the 4 states that we want. If the deadline passed and the redeemer is 0, it should be approved. It's in green. But any other combination, it should fail. So let's actually write the test for these 4 combinations, which are the ones that we care about. It shouldn't be like, I'm guessing you will figure out that if we test only on this side, we have no idea if these other quadrants are going to actually pass the transaction. So we have to check all of them. So let's write the test. The tests are really simple to write. There are just functions that, if they are unit tests, take no parameters. And instead of using the fn keyword, we use the test keyword. And then we define a function. So we can use negative redeemer after the deadline. Success. Succeeds. We want to test this. If we provide negative redeemer after the deadline, it should succeed. So let's create the context. Context is equal to the function we just defined, create context. And we can pass here the transaction lower bound, and we're going to pass like 100. The value itself only matters if relative to the deadline. So let's define the deadline. And we need to let's run the actual validator. So if we go to the validator, it's called negative earth time, takes datum, redeemer, and context. So let's say, okay, negative earth time, and we have to provide the datum. The datum is the custom datum, so we can just create one right here. Custom datum with the deadline of, and here we have to provide a deadline that is smaller than the time when we create the transaction. So we chose the transaction to be submitted at the 100th POSIX time. So we want to put the deadline smaller than that, for example, 50. And then we have to provide the redeemer. We said that we want to provide the negative redeemer, so we just like -1 as well. And then we need to provide the context. We just created the context, so we can use it right here. And that's it. We have our first test. And we can like run this test right now to make sure that it works. Let's open a new terminal. And to run both the type checker and the test at the same time, we can run aiken check. But I think that if I run this right now, it's going to output a bunch of stuff. Let's do it anyway. Yeah, so we have a bunch of tests for other things that we've been, because before like before teaching, we have to test that everything is fine, of course. So we have another way. Those were like the whole, like if you want to run everything or like the test for all your validators, you can do that, but you can target the validator. So if we run aiken check help, it doesn't help at all. Because check, there you go. So we have all these flags with aiken check, and one that is in this specific time useful is the M or match test that allows us to choose a specific validator that we want to test. So we can use ACAN. Oh, let me hide this. ACAN check and -m, and now as a string we're going to provide lesson 4 negative are timed. And if we do that, it's going to run only the negative airtime validator test. And as you can see, it's going to give us a bunch of really useful information. So here we have the thing that we tested, this validator. We have the test that is called negative redeemer after deadline succeeds. We see that the test passed, and we see the memory and CPU units that the validator used. And these memories or CPU units are actually the ones that are going to be used in the blockchain. So it's like, if you want to make sure, like, if you want to check how much it will cost to run the validator, this is how you can check that. And here we have like a summary. We have a summary for this particular validator that says we run one test, 1 was passed and 0 failed. And this summary is for all validators. In our case, we just have 1, so it's the same. 1 check, 0 error, 0 warnings. And this is how you can test validators, unit test validators. So now we can keep going. We can say, okay, we have one test of 1. We check this quadrant, but we need to check the other 3. So let's run the other 3. So we have a negative redeemer before deadline. Before deadline should fail. And in this case, the only thing you need to do is like the transaction is executed at the same time, but I can change the deadline to like 150. So now all of a sudden I'm running the transaction before the deadline. And if the redeemer is negative or positive, like, doesn't matter. If I just do this, if I run this test, I know that it should fail, but I'm not telling the test suite that it should fail. And for that, we have a specific keyword called fail. So if we indicate, if we use this keyword right here, we said this validator should fail. And if it fails, that's good. That's what I'm looking for. So if we run again the checks, we see that we have the same thing as before with the same memory, but we have the new test, negative redeemer before deadline fails. And we have the reason that why it fails. We have the trace that says, hey, it's after the deadline, should be true, but it's false. So we not only get the information that it fails, but we also get the information why it fails. It's because of the deadline, not because of the redeemer. And we can keep going. Negative redeemer, we can say positive redeemer. Actually, it doesn't matter, but after deadline fails, you add an S. And in this case, we have the correct deadline, but because the redeemer is positive, it should fail. So we can check this. And there you go. As you can see, positive redeemer after deadline fails with the trace that redeemer is equal to 0 ended up being false. It should be true because we indicated that this should be false. The actual test passed. If we didn't provide this fail, the test suite will assume that this should pass. So let's actually run this to see how it looks when it fails. There you go. So now we have is this fail because you said that it needed to return true, but it returned false. And this is why it returned false. The redeemer is equal to 0 is less or equal to 0 is not true. This is how it looks when it fails. But for now, we are all good. And we need positive redeemer before the deadline. And we have the positive redeemer right here, but the deadline is. And that's it. So if we run this. Awesome. So all our 4 tests passed, and we checked the 4 quadrants that we care about. Any questions so far? I think maybe we should, if you have any questions, we're going to move to property testing. Maybe I'm going to do that before the break. Yes. Let's do property testing first before the break. But before, if there's
I have one question to you. Are you aware of the placeholder function in the transaction library?
Yes.
Okay.
Yes. But I found out after writing the test, and then I didn't know if I could change the values, or it was just.
Yeah, you can.
Yes.
So you can just, it's like, you can do transaction.placeholder validity range equals whatever. So you can use it as a template and then only change the values you want to change.
So I can just say placeholder.
Yeah. And then yes, you can say that, and then you can, for example,
no, yes, transaction interval. No, it wasn't transaction interval. It's validity range.
Right.
We do that.
I don't know why it's complaining now.
I know that.
I think it's. Hang on, let me just check. Because I saw in the documentation that they do it. Just a second.
Yes, I'm going to open the documentation as well. So if we go to transaction at the bottom. That's why I didn't try.
Yeah.
Yes, because I'm not sure if you can actually modify the values or just see them.
That's a good question. Oh yeah, sorry. So I mislooked, but surely you must be, otherwise it wouldn't be useful, right? Isn't there? Hang on, I think there's another example. So in the documentation it's not clear, but
maybe in the here. No.
If you look, hang on. If you look in, I can paste the link. Sorry, I'm not good with icon yet, but sorry, I just pasted a link here in the chat.
Yep.
It's this walk through, and there.
And let's see.
I'm not. Hang on. Are you sharing?
Sorry,
yeah, it's a bit small, but for me. But you go down a bit.
Placeholder.
If you scroll down a bit more. There, in this. Sorry.
Yes, here.
now it's on top of your screen. Now it's in the middle of your screen. So somehow he builds this function and then uses function composition. And there seems to be this syntax there with the curly
Oh,
brackets, whatever.
I see. Yes. Yes, it makes sense. Perfect. So I'm going to do that right now. Okay, so I can just create this placeholder, let's say like this, placeholder. And here, instead of doing all this, I can just say transactions equals placeholder and the spread operator. Spread operator. I think it's 2 dots. Yeah, transaction. Oh yes, no, because it shouldn't be here. It should be in the here.
And then 2 dots, I think, oder?
Yes, 2 dots. So I have to use this validity range. Let's do it right now. Validity range equals transaction interval. And now I can use placeholder and spread it. And if I do this, I can remove
Yeah, I think like this.
something like this, but
I need the constructor, yes.
it worked. Awesome. Yes, I saw that in the documentation, but it was too late to change it, so I just ignored that. But yes, awesome. So
this
Yeah.
placeholder is basically a transaction that has everything trivial fields, so empty lists and nulls and
yes,
so you don't have to. Robertino had to write quite a lot to set all the fields that we are not interested in. But with this, you basically can concentrate on just setting the fields you are interested in, and this placeholder gives you default values for the rest.
I'm going to just to be clear.
Mhm.
Yeah, so yes, these are not mutable, but you can use the spread operator to like put everything that is in the default, and then if you redefine specific fields, they are going to be changed for the result of this operator. So the script context, the final script context. Awesome. Okay. Thank you, Lars.
Welcome.
So
Always eager to find ways to be lazy.
okay, so let's just run this again. And we have these warnings because we're not using a couple of things. There you go. Perfect. So let's do property testing. Anyone has any questions?
No, in the chat.
No.
No. You want to take a break or you want to continue with the property test?
Yeah, sure. We can take a break. Yes. Let's do 2 breaks because then I have to start with the Oracle. No, not the Oracle, but the swap contract, and that's going to take a bit.
Okay.
Okay, 10 until 20.
Okay.
Okay. Okay.
Thanks.
See you, everyone.
Then.
Okay. Hi, everyone. Are we ready to go? Awesome. Okay, so far so good. We have our contract, we have our unit tests, but if we're being honest, we're not checking what we really care about. We don't really care about like these specific points that it works or not, because someone else can just try this point or this point or this point or the other combinations. So what we ideally would like is something like this. So we would like to test everything, basically. On all sides. And we want to make sure that the result looks like this. So this is what we ideally will want to, right? We could approximate this quite successfully with unit tests. We already covered unit tests in the Haskell section, but just in case, I'm going to like cover only the concept. So when we provide unit tests, we provide specific values that we want to check. In this case, we provide like the transaction debt, and we provide the deadline, and we provide the redeemer, and we check only for this. We ideally will want to check for all of them, for all possible combinations. That's not feasible, but we can do both in Haskell and Aiken, is to generate randomly all the a huge amount of points. So like at least it approximates what we're looking right here, like with enough confidence that we can move forward, that saying that this works, right? And in this case, we call these properties. We say, instead of saying, hey, the validator like accepts the transaction when this and that, we say the validator has the property that for anything before the deadline, it will fail, for example. And we express that property, same as we did with Quick Check. And then we leave, like we ask the Aiken tooling to generate a bunch of test cases, and if it finds an error, it will shrink it to make it easy for us to understand what's going on, what's wrong. So let's do that. We don't have currently, as with what we covered so far, a library to generate, like we have the building blocks, but not really. Like we need some library that provides generators and shrinkers, so we don't have to worry about that. We just want to write tests. Luckily, Aiken has that. If we open Aiken Fuzz library in GitHub, Fuzz. Let's see, it's right here. So in the official repository of Aiken, we have the Fuzz library, and this is the official library for writing fuzzers, which they are just generators for Aiken smart contracts. So this is the first time that we're going to actually use something that doesn't come like built in, like the standard library and the built-in code. In this case, we're going to use a different a different library, and so we have to add it to our dependencies. So for that, I think I already have that, but it's really easy to do. So if we go to the TOML, the Aiken TOML file, that is the Aiken TOML file is in the root directory. We go right here, and for some reason doesn't have syntax highlight. Let's see if I can. So for some reason we don't have. I mean, we can just use regular TOML syntax highlight, I think. So we have nice syntax highlight. And if we don't, this is small enough, so we can just, there you go. So we already saw this in the first lecture, but now we had this dependency of the standard library that was already pre-written for us. But now we need to use the Aiken FOSS library. Usually you can just do the same procedure, like the name is the place in GitHub, like the organization and the repository. The source is GitHub, but it could be somewhere else. And then in the version, you could use like numbers. But in this case, because the library is really new, I just chose to pinpoint a specific hash that it was 2 weeks ago. If we go to commits, we see that EDCFA. So this is the specific commit that we're going to use using the FASM library. And once you do that, that's it. Like Aiken will pick up on that, and when you build and run tests, we'll figure out that it needs to download and install the FOSS library. So once we have that, we can start using the fuzzers, the generators, to write our tests. So if we go to the property test, we can say, okay, let's test the property that all redeemers fail before the deadline. We have to use the same test keyword because we're testing, and we have to provide the name of the function. In this case, we're going to name property anything before deadline fails. But in this case, like this, so far, this will be a unit test. But the difference is that for property test, we can provide as an argument the fuzzer, the value with the fuzzer that we want to use. For example, just as an example, we can say number. This number is going to be of type int, and here's when we use the fuzzer. We use the via keyword, which indicates that we're going to generate this number via a fuzzer. And then we can use the fuzz. We can use the fuzz library and say, for example, we want integers, so we are going to use the int fuzzer. And we have to import. And there you go. Now, when we run the checks, we're going to see that Aiken is going to provide this number of a value of type int via this fuzzer randomly. So we can actually test. We can say n is bigger than 0, and if we run this, it's not n, is num. And if we check, we see that it failed. It failed after 7 tests. So the Aiken test suite tried 6 times. Ended up being like trying 6 different times negative numbers. But then at the 7th time, it tried a positive number or the 0, and then it reduced it, shrinked it into 0, which is like the simplest thing that you can do basically as a counterexample. And if we can, for example, say number bigger or equal to 0 and run again, and now as a counterexample, we get -1. So, and that's pretty much it. That's like the main way to use test. We can, of course, add more. We'll see how we can improve on test later in the number of tests. But for now, this is the new part. Basically, we use the via fuzz, and now we actually provide a value to the testing. Prior to this, we couldn't, because unit tests have to take 0 parameters and property tests have to take specifically 1 parameter. Now, we don't need this number. We need the deadline and the redeemer, because these are like the 2 values that we care about. But the thing is, if we try to say redeemer and then the deadline, we'll see that we as found deadline means, well, the error is not really helpful. But the thing is, we cannot provide 2 parameters. We cannot generate 2 parameters separately. They provide 2 parameters separately for the test, for the property test. So we have to do something else. And if we go to localhost, shouldn't we have vesting negative uptime? Standard live items somewhere. Let's see if I type fast. Yes. So I had to write the name of the library, but if in the documentation that you generate using Aiken docs, you like actually enter you can see not only the things that you generate, but also all the documentation of all the libraries that you depend on. So we have this introduction to Aiken Fuzz, but if we go to the Aiken Fuzz modules, we will see all the functions that we have at our disposal. So we have to generate booleans, we can generate bytes, byte array, constant, either int, which is the one we're using right now, etc., etc. So we have a bunch of things. The one that we care about right now it was right at the beginning, I think. Yes, it's this one. It's both. Both allows us to combine two fuzzers in a two-tuple, in a pair. And this is exactly what we need, because we cannot provide 2 different fuzzers to the testing library, but we can provide one fuzzer that is a combination of 2 different fuzzers. It's exactly what we need. So we're going to do just that. So let's see. We want to provide this value that is going to be let me delete this. Let me delete everything. No, not everything, like just this. So as a parameter, we want to provide a value that is going to be a tuple of ints that is going to be the deadline, and another int that is going to be the redeemer, via a pass both. So we are combining two right now. And now we have to provide the first one. So the first one, they are both ints, but they are not the same. So if we go fast, that's int. If we do this, in this case, we're going to get as a like transaction earliest time. As a time, we're going to get both negative and positive number randomly. So we want to know what's the maximum value because we want to put the deadline like in based on that. We want to choose a deadline that is before or after whatever is generated by the fuzzer. So what we could do is if we go here and to the ints, we have ints, we have at least, at most, this will be useful, the int at most, and we could put here whatever like maximum value we want. But because we know that we're dealing with POSIX time, we know that it cannot be 0 or negative. Like we know that we are after 1970. So we can just do the in-between and save ourselves the testing negative numbers, which are, it's obvious that we are not going to encounter in the real world, right? So let's use this in-between and provide the minimum and the maximum integers. This is going to generate uniformly the values. So int between, and the minimum is going to be 0, and the maximum we could do whatever we want as long as it's smaller than the deadline. So let's say that the deadline is in here before we chose 100 as the transaction time and 150 as the deadline and numbers of that size, because we were testing a specific point in time. But if we do that again, if we choose 100 and 150, for example, and we run 1,000 tests, we may exhaust like not all the combinations, but we may exhaust all the like specific time range combinations. So maybe if we do 10,000 or something like that, or we will repeating the test like often or stuff like that, the deadline often, stuff like that. So the solution to this is to use bigger ranges. We're going to increase the range of time just to make sure that we don't get a collision. So let's say we're going to generate from 0 to 9,999, for example. So we're going to create transactions from 0 to 9,999 POSIX time. And we have our first fuzzer, but our first generator, but we need another one. So in this case, we need to generate the redeemer, and we said right in the name of the function that anything before the deadline fails. So we don't want to restrict the redeemer in any way. We just want like anything that can be possible. That's good. That's good on me. So let's use int, and this should be good. And that was it. So that's the new part right here. This is the difference between unit and property test. There are some caveats that we're going to talk about now, but like if you understood so far how we can obtain and combine this, it's likely that you have types that are generated combining multiple simpler types. So you will need this either, you will need the both and other forms of combination, and then this one is really useful as well. But this is like the key difference. And now that we have this, we can say, okay, let's extract this tx earliest time and redeemer, and this is we're going to pattern match the validator, the value. Sorry, we're going to patch this value that we get from the generator, and we have to actually construct the transaction. As if we see, like in the previous test, unit test, is the same. So we can actually copy and paste if we want. We have the earliest time the redeemer, so now we created the context of the transaction, but in this case, we have, instead of hard coding it, we provide the earliest time. And as a deadline here, we know that we want to test anything before the deadline. And we know as well that we are going to create transactions for 0 to 9,999. So I'm just too lazy. So I'm going to change the deadline to 10,000. So it doesn't matter which number is generated. It's going to be always before our 10,000 POSIX time deadline. Make sense? We still need, though, to change the redeemer from the hard-coded one to the one that we generate. And if we save, there you go. We have our property test. We can run it. Of course, it's going to return an error because in no point I'm saying that this is just the name of the function says that this, and we know that it should fail, but we are not telling Aiken that it should fail. So if we run this, it will give us an fail error. Yes, it's going to deprop anything before the deadline fails with the counterexample of 0 and 0. And the trace that we have is that is after deadline should be true, but it's actually false. So how do we tell Aiken that we want this to fail, and if it fails, that's good? We can use, same as before, the fail keyword right here. And if we do that, we get that it fails, and it says, hey, it failed, that's good, it should fail. And it gives us the counterexample that 0 and 0 fail, and why it failed is deadline, it's false, and all good. But there's an issue here. I'm not sure if you spotted the issue, but the issue is that it says right here after 2 tests. So as soon as it finds a counterexample, Aiken stops testing. So it behaves a bit differently than you might think intuitively. You will think that it keeps going, and it keeps going, it keeps going, it keeps going, like, and everything should fail, nothing should pass. But actually, it's like it tries stuff until something fails, and then it says, okay, I found something that fails, so good. We don't want this because we have just 2 tests. We have no coverage at all. We just have right here, we have like 2 points instead of the whole range. So how can we do that? Well, it's pretty easy, really. We're just going to say that this should succeed, the actual test should succeed, and we're going to change the Boolean here from false, we're going to toggle the Boolean. If it's positive, if it's true, it's going to return false. If it's false, it's going to return true. So if we do this, we'll see that it's going to keep trying and keep trying until the amount of test maximum that we define, that by default are 100. And every time the negative error time is going to return false, and we're going to toggle it to true. So the test is going to pass. So let's save this. This is a small but significant detail. There you go. So as you can see, we have, hey, it passed after 100 tests. So now it starts to make sense. So now we have a bunch of randomly generated numbers, and these values, this is tested 100 times, which is not like the best, but it's good enough. We can actually change that. We can change the amount of passes that we do, the amount of of values that we generate in our random walk. And we can say, if we check and check help, we see here max success, maximum number of successful test runs for considered property-based test valid. The false is 100. So we have max success. So we say max success equals to, and now instead of 100, we can say 1,000, for example. It's testing. There you go. And now the property tests 100,000, like 1,000 times the property, and all 1,000 tests passed, so the property passed. Make sense? Any questions so far? We're going to keep moving with the other properties, but just in case.
No in the chat.
Okay, so let's keep going. That's one property that anything before the deadline fails. That means that we have right here, we have the deadline. So we just checked these two red squares. So we checked redeemers both positive and negative, but everything before the deadline. Now we need to check redeemer positive after deadline and redeemer negative after deadline. So let's do that. Test. We're going to test the property of positive. Let's see here. Positive redeemer after the deadline fails as well. Positive redeemer after deadline fails because we check right here. No, we check right here that the redeemer should be less or equal to 0. So property positive redeemer after deadline fails. The name is a bit long and clunky, but it makes sense because then we're going to see here the name, and it has to be descriptive enough so we know like what's being tested there. So property that positive redeemer after deadline should fail. So we need random values. What do? We just take them from the same place, like we just have to generate them again. And actually, we can, if we want, if this generator will be equal to this generator, we could create like function my father and return this. And then we could use my fuzzer instead of this whole expression here. So we can just say via okay. My fuzzer, and that's it. And that will work. But the thing is, these numbers change. So, and not only these numbers, but also like these properties, you will see that they change. So it's not useful to extract the fuzzer away, but just know that you can do that. If you have a really complex expression combining fuzzers, you can just define a new one. You just have to make sure that it works as expected. But once you do that, you can keep going. In our case, we cannot extract this, doesn't make sense, because we have to change these properties. So we said positive redeemer after the deadline fails. So we said that the deadline is 10,000, so we're going to keep that. So now we want to generate, instead of from 0 to 9,999, we want to generate int, and this is int at least generate a random integer with at least the minimum value. So for example, int at least, and we're going to provide 10,001 just in case. So we're going to there we go. So this part, actually, like the body of the function, we can just reuse it. We are not changing the body of the function. We are just changing the fuzzing, the values that will generate. Actually, we could, if you want, you could extract this as a, because it's repeated the whole time. We should do that, but after we finish the tests. So we have positive redeemer after deadline. So we have the deadline of 10,000, and we're going to generate the transactions in the times at least 10,001 upwards. So we could have like huge transactions, huge times, years from now. It doesn't matter. It doesn't have an upper limit. But the integer I really care about, because now I cannot provide any redeemer, because if it's negative, it's going to pass. If it's positive, it's going to fail. And that's like different properties, right? So in our case, we want to choose either one or the other, and we chose positive. So we're going to use the same thing that we just used right here. So we say fuzz int at least 1, because 0, as we saw before, 0 also is valid. So at least 1 of POSIX time, and that's it. I think positive redeemer after the deadline fails. That's it. This I'm indicating right here with the not that this should return negative. It should return false, so we can change it to positive. And if we run it, we see that again, it passes all the 1,000 tests, both anything before deadline and after deadline fails. We need to check one last thing. So we checked with the first property everything before deadline, the second property after the deadline positive redeemer, and we need to check the final after deadline negative redeemer. I think you could just do this by yourself by now, but just do it. Negative redeemer after the deadline should see We have to change so many p's. Change negative redeemer after deadline. So see, and this is bothering me. Sorry, fails. So now the only thing we need to change is what we need to change. Someone can guess? We need to provide a negative redeemer after the deadline. What can we do? Any guesses? Let me put this. What can we do right here? So the deadline, we need after the deadline, and the deadline is 10,000, and we are generating numbers bigger than the deadline. So our transaction is going to be after the deadline for sure. But the redeemer, on the other hand, needs to be negative, and we are saying that and we are generating 1 or bigger. So we need to change the redeemer. And if we come right here, we can use the int at most, which is like generate random integers at most this value. So that's the change we need to do. Int at most, and at most, for some reason it doesn't change. There you go. And at most 0, because we want to check all negative numbers with 0 include as check. And that's it. Now, but if we run this as it is, it will fail, because like this is good, like this is after the deadline, and this is a negative redeemer, so that's good. So after two tests, why it failed? Because we keep telling that it should fail, but in this case it should succeed. So we have to remove the toggle of the boolean, and now this should be fine. There you go. So we have 3 property tests, each test 1,000 different times with different values. And we could extract this expression. For example, we can say function test val with this, and we can provide the val int and returns a bool int and returns a boolean. And now we can say test val with this val. We can remove right here and right here. There you go. And those are all our property tests that keep passing. That's it. Any questions so far? Okay. So there's one more thing that is really important that you have to check, but it's a bit cumbersome. It's not as easy as with Haskell, believe it or not, which is you will want usually to check if the value that are being generated. If we open the tests, you will see that if everything passes, we have no idea of why. I mean, they are all passed, okay, they were all correct, but we have no idea of what we checked. So we have no idea if the generator is actually generating something that is not really being helpful. So for that, you can do specifically, we have this fuzz that label, I think it was fuzz that label, and if let's look late. Oh, it's right there. So label collects the properties that we are checking, and prints the whatever it collected, depending of the logic that we wrote like inside the label, right? So in our case, we can say label if redeemer is bigger than 0, bigger than, let's say, just to be consistent, smaller or equal than 0. In that case, we're going to return the string. We use the at to indicate that this is a UTF-8 string. Negative redeem. Else, we positive redeemer. So now that we add this label, every time we use this test val, which is in all tests, we are going to label which redeemer, like the amount of redeemers that were negative and the amount of redeemers that were positive. So if we run this, we see that for the first property, anything before deadline fails, we see that we have a 75% of positive redeemers and 24% of negative redeemers. And then from the positive redeemer, after deadline, we see that it's 100% positive redeemer, exactly what we want. And for the prop negative redeemer is 100% negative redeemer. It's exactly what we want. So this is how you can, like using the label, using like multiple times and in different ways, you can collect the values that you care about to have like some insight of what is being generated. And that will be it as an introduction to testing in Aiken and to property testing in Aiken in general. We have another example, which is a bit more realistic, which is a swap validator. Not sure if we should, I don't recall. No, it's not, it's too early. We were back at 20. So I think we should do a bit more before taking another break. So any questions so far?
No, in the chat.
Thank you, Karina.
None at the moment.
Yes. Sorry, Muchi. Muchi, I didn't understood.
Sorry, I meant I don't have a question at the moment.
Awesome. Perfect. Thank you. If you happen to have in the future, just interrupt. It's okay by me. So we have property test. Yes.
It's okay. You can.
Awesome. Okay, so let's move into a more interesting scenario. I'm going to I'm going to leave this maybe written so we don't have to write all this, but I'm going to let's go down to that datum. There you go. So we have a bunch of warnings because I just deleted a bunch of code, but not all of the code because I want to I don't want to rewrite this validator since you already likely know everything you need to actually code this validator. I can list and value. There you go. So we have this swap validator, and let me draw a picture here. So this is the thing. We want to sell some tokens, an NFT or multiple different NFTs or tokens. And what can we do in the blockchain without a smart contract? So we can just talk with someone, say, hey, how's it going? I'm going to sell this NFT. And the person say, for sure, let's do that. Just send me NFT, I will send you the money. And you send the NFT and you never hear about that guy again. So you cannot go back. You cannot recover money. You cannot go back in time in blockchains if the transaction has been confirmed with enough blocks. So you're screwed basically. So you cannot send the NFT first because then the other person could just go away, and the other person cannot send the money first because you could go away. The other person has no idea if you're going to do that or not. So we're in a stalemate that no one wants to send the asset first. So what can we do now? Well, we could write a smart contract that locks the asset and releases the asset only if, and in the same transaction, you are paying to me something. So imagine that here we create with a transaction. It's going to be empty. We create a transaction, and in this transaction, these transactions generates the output between, there are other outputs, but there's a specific output that is generated by the transaction. That is the one that we care about. And this output is sitting on a swap contract. So we can be right here. Seller wallet. This UTXO is in the seller wallet, and it contains value, an NFT, and other stuff. Value. So the value in the seller's wallet contains a bunch of stuff, but in particular an NFT. So what we can do is we can create a transaction that consumes this UTXO, generates two UTXOs, generates one UTXO, one UTXO that has the swap contract. Inside this swap contract, we have as a value the NFT, and as a change, you get back all your other assets, all your other stuff, except for the NFT that now is locked into this contract. So this is the first transaction. Why do we do this? Well, because if I have things in my wallet, I'm the only one that can consume consume this UTXO and use it somewhere else, right? But I need a way for someone else to take that NFT if only that person also sends me money to my wallet. So we create the smart contract that does this is we're going to call swap contract, and this swap contract is going to hold my NFT and a bunch of rules. These rules have to enforce that if someone wants to consume this UTXO, needs to pay something to me. So let's say that this smart contract we're going to save in the datum. In the datum, we're going to say, okay, I'm going to sell for example, a seller wallet address. Want to sell this thing that is locked by the UTXO for a specific price. So we can put that in the datum. We can say this is the seller, the person that created the UTXO, because someone else could also generate their own UTXO in the swap contract. So in the datum, we're going to say who is the owner of this NFT and what's the price that the owner is willing to sell the NFT for. And then once we have the UTXO, that UTXO can only be taken if in a separate transaction, we can say second transaction. In the second transaction, some buyer wallet, some buyer is going to use his own money, buyer wallet, and here we're going to say as with value, the buyer has as a value, sorry, more than enough, more ADA than the price of the NFT. Make sense? So, and now there's a buyer that says, okay, I have enough ADA to purchase it, and I want that NFT. So that buyer is going to create a transaction, is going to provide a UTXO in his possession that has more than enough ADA to pay for the NFT, and it's going to consume this UTXO at the swap contract. And then it's going to generate, let's say seller wallet. And then it's going to generate two UTXOs. One for the seller, that the seller is going to have value, price, the seller asked for. So it's going to send this, the buyer is going to create the transaction that consumes the swap in his own wallet, in his own UTXO, and generates a new it generates two UTXO, one for the seller containing the price that the seller specified that wanted to be paid. And let's see, let's open this, trace this. And another UTXO for himself or herself that now has less ADA because it paid for whatever this was sent to the seller wallet, less ADA, and the NFT. So this is the whole process of a swap contract. In this way, you can be sure that you are going to get paid, because if this buyer doesn't create the UTXO in your wallet, like for you, with the value that we specify right here, that you specify initially right here, this transaction will fail because the smart contract is going to deny the transaction. It's going to return false. It's going to fail the transaction. Make sense? Now we're going to see how the logic of the swap contract is executed, but the overall idea makes sense. Anyone has questions? Okay. So let's see what we have to write here in the swap contract to make sure that this buyer cannot just take the money, take the NFT or the tokens or whatever it's locked in there. So I call this exploitable swap because reasons, secret reasons. But yes, this could be called like a swap contract. I call this exploitable swap because we can do something to exploit this contract. So the exploitable swap takes the datum, and the datum, as we see right here, it contains the beneficiary, public key hash, this verification key that we use many times before, and the price. So this is locked in the UTXO datum. Who needs to be paid and how much in the price. As redeemer, we don't provide anything. We don't need to provide a redeemer. And as context, we have to provide, we need the script context to check for the outputs of the transaction. Remember that the swap contract needs to check the outputs of the transaction, not only inputs, not only time. Actually, we don't care about time this time. Remember that the context of the transaction has access to both inputs and outputs. So we want to check in this case that this output is present and the price is correct, is at least what we asked. So let's start. We say, okay, we want to spend a UTXO. We want to spend this UTXO. And if we first get the outputs, we say, okay, we know that inside the transaction, we have the outputs of the transaction. So we just pattern match to extract it. Then we want to check from all these outputs, because this transaction could be like generating 100 outputs. I don't know. I have no idea what's doing. But from all of those outputs, I want to check only the ones that are meant to be for the seller, which is the beneficiary of the beneficiary of the transaction, who gets paid the seller. So I'm going to filter all the outputs to only the ones that are meant to be the beneficiary. How do I do that? Well, I use the filter function from list, and the filter function takes a list and a function that does the filtering. So we provide the outputs, and then we create the function, this anonymous function, that takes for each output, I check the output address, and that output address has to be equal to the address that we get if we get the datum.beneficiary, meaning the seller. We use this from verification key. Let's see if we have any. No, we don't have any explanation there. So let's go to the docs. No, this is fast. It's not a library. From verification key. So from verification key, this we already provide this in the datum. So we have this, we have the verification key. It's the hashed verification key. So this from verification key takes the hash, the pool key hash, and returns the address. So all we need to do, the address is, it tells me where the UTXO, this UTXO is going to be sitting after the transaction. So all I need to do is to check that the output, the address where the output is going to be there, is equal to the address of the beneficiary, the seller. So after doing this filtering, this user outputs value is going to be a list of outputs that are only meant for the beneficiary. So I got rid of all the other outputs. And then what happens? Well, imagine I could, if potentially, I could just send everything in a single, I could just create a single UTXO with all the money, and that's it. But I could also, like the buyer could also generate the transaction where it generates more. Let's see here. There we go. So it generates more outputs, not just one for the seller, for the beneficiary, but it has, for example, in this case, there are two. So it's half the price the seller asked for, and half the price the seller asked. So in this scenario, we are paying everything the seller asks for, the beneficiary asks for, but not in a single UTXO, but in a multiple. We provide half in this and half of this for some reason. I don't know. But if we are the seller, if we are the beneficiary, we don't want to deny someone that to pay us the total amount just because it's paying in like separate UTXOs. Like we don't care if there's a single UTXO, separate UTXOs. If it's enough ADA, we don't really care about that. So what we do is, okay, imagine that we have more than one. Well, in this case, these user outputs will have more than one output. So we have to calculate the total value sent to the seller. And we can use fold left, which works the same as Haskell's, but it's strict. So we can use fold L, and if just in case you forgot already, fold L you shouldn't, but just in case you forgot, fold elf takes, this one is in dictionary, but we are in list. Let's see, fold L list. So it folds a list starting from the a base value and with a specific function that combines like the accumulator with every value of the list. So that's what we're going to do now. So we're going to fold the list. Which list? The user outputs list. We're going to start with value 0. And if we go to here, we already saw this, I think, 0, just in case, value. 0 is an empty value with nothing in it. So we have like nothing, we start from nothing. And then for each element, we are going to take the element and the accumulator, which starts being 0. And we're going to merge the values for each output. This n is an output. Maybe we could do output like this. So we're going to merge the value of each output with the accumulator, and we'll eventually, let's see, merge. It's right here. Well, yeah, merge. Combine two values together. So it's like semi-group operation. If you remember from Haskell, it just merges it combines them. It's a binary operation that combines the values. So it's a semi-group. And if we do that for all the values, we'll eventually get a single output that is called a single output. That is the value paid to the beneficiary, the total value paid to the beneficiary. And now that we have this value, we need to check that the value is bigger or equal than the price that the beneficiary needs to be paid. So we check that the value, if a value is the price is of type integer, it's an int, but the value is not an int, it's something of type value. So we can use this function Loveless of, specialized versions of quantity of for the ADA currency. So this Loveless of function gives us the amount, takes a value and returns an integer of only the ADA inside that value, ignoring other tokens. So we use the Loveless of to get an integer that represents the amount of ADA that got paid, and we check that that's bigger or equal than the price that we provided in the data. So if we do that, we should this should work, right? The first transaction is created by the seller, but the first transaction just sends money to the swap contract address, so that is not something we need to check. And the second transaction consumes for the smart contract, and the smart contract checks, hey, let's see, you want to get this NFT? Well, I have this price and this seller address. Are you creating outputs in the seller wallet that add in total as much as the price specified by the seller? If you are generating these outputs, you can consume the NFT and you can do whatever you want with NFT. I don't care. I just care that the seller is getting paid. And that's it. So that's the swap contract so far. It seems logical, right? I mean, it seems like it should work. So let's test it. I think this is going to, we're going to need to create a bunch of helper functions. Yes, let's do that quickly. I'm not sure if I should, because we don't have much time, so maybe I can go over the code instead of writing it from scratch. I can do that quickly though. No, just in case. Yeah, we won't have time for me to write everything from scratch, so I'm going to undelete everything that I just deleted. Don't get too scared with the amount of code. There you go. So we need to create a couple of testing helper functions. So we need to create a context again. In our case, actually, let's transaction. We already saw that we don't need to do this. Transaction equals placeholder. No. Actually, I can just do it right here. Transaction placeholder, and I can just spread right here and say I only in this specific case I only care about the inputs that, as you can see, I'm passing to the create context inputs in out and the outputs out, and I think this should work. Let's delete this to see. We have to import it. Yeah. So we have the create context function, and in this case, we don't care about time. We don't care about who signs the transaction. I don't care who signs it. I only care what goes in and what goes out. So I'm going to provide as parameters a list of inputs that the transaction is going to consume and a list of outputs that transaction is going to generate. Then we're going to see how we create these inputs and outputs, but we have them. And with that, I'm going to create a script context. Then I'm going to pattern match on the first. I'm going to take the head of the first input. I know that this is not going to fail because I'm creating the list and I'm going to put at least one input. So I'm going to create this to get the output reference. That's just to provide some output reference. As you can see in the top right here, I'm not using it. I'm not using the output reference, but I need to provide one to create the type. So I just take the first one. I don't care. I just take the first one and provide as the output reference of the purpose, and create a placeholder transactions, placeholder transaction that has everything default except for the inputs and outputs. Okay, so now we want a specific input. We want this input to be somewhere. We want to consume a specific input. So we have to create this swap contract input. So we create using the input constructor, and the input constructor, let's see, takes an output reference and an output takes address, value, datum, and reference script. So we have to fill all that. So the input takes an output reference. The output reference, I'm going to just fill some random transaction ID with just random hash. and a specific index. Like the index is parameterized because I said so. For now, you will see that later. So we have this create swap input, and we have the reference and the output, and this output is what is contained in this input. So we have the address of the output, some random address, but important is a script address. So this 96, should be in the real world when you're actually running this in the blockchain, the hash of the script that we just wrote, the swap script. And we use the from script function to translate this hash into the address of the script. Then we need to create some values. Like we want to sell some token. So let's just create a fake token. So I created this create fake asset function that takes the name and the amount and creates the assets, creates a bunch of fake assets. And if we navigate, it doesn't have navigation. So let's go here. We have the create fake asset that takes an asset name, that's a byte array, and the quantity. And then the from asset function, we provide the policy ID, the asset name, and the quantity, and we get a value back. We are going to just hard code some random policy ID. Remember that this doesn't matter because we are not checking this in the validator. We can just put gibberish here because the validator doesn't care. But if the validator checks this at some point for some reason, we have to provide a proper value, or at least a consistent value throughout the checks. So we get this random policy ID, the asset name that we just passed, and the quantity that we just passed, and this returns a value. So if we go back, so the swap input has this address, contains 5 fake token name. Maybe we could say Cardano calls ABC. So this is the token name now, Cardano calls ABC, and we're going to mint 5 of these tokens. We're going to sell 5 of these tokens. We can just do 1, so it's not necessarily it's an NFT, but we can just say that is now the Cardano calls ABC NFT. NFT. We provide no datum because we're not using it, and there's no reference script because we're not using a reference script, and we have to talk about this eventually. So we have an input that we're going to consume. That is the input that is going to be sitting in the validator. Then we need, we have the swap input, we have the beneficiary output. So far, so good. We have the context of the transaction, good. We have the input that we want to consume, good. Now we want to create the output that we want to send to the money. And that's easier. We have to feel the same as before, but in this case, instead of from script, we use the from verification key, and we pass as a parameter the beneficiary. We're going to provide the key of the beneficiary, and that's important. That's not any random stuff that we can hard code, because then we check against this key. So we have to be sure that this beneficiary key is the correct one. Then as value, we can use this from logless function that takes an integer and returns a value. So we're going to, as a value, we're going to provide this whatever the beneficiary asks as a price, no datum, and no reference script. So here, same as this input is the one that represents the swap contract and has all the correct values. This output is the one that represents all the interests of the seller after the transaction. So it has to be sent specifically to the beneficiary, and it has to contain specifically the price that the beneficiary asked for. This cannot be like any random value. It has to be specific this if you want to actually validate the transaction. Okay, that's it for helper functions. This create asset, we have create fake asset, where you saw, and yeah, we have the create dummy output, which is something like we want to check what happens if I don't create this UTX. So what happens if I just like take the NFT and don't pay the owner? So for that, we're going to create a dummy output. That is an output that comes like somewhere else. I don't care. Like it's from somewhere else and it has some other data. So when I create this output, the beneficiary, the seller, is not getting paid anything. So let's actually create the test. Let's do some unit testing. So let's try to do the honest transaction. So let's say that the beneficiary has a key of 1, 2, 3, 4, 5, 6, and ask for 100 Lovelesses for these 5 Cardano Course ABC. Let's use tokens, because later we're going to use more outputs. So let's say that this person wants to sell 5 Cardano Course ABC tokens for the price of 100 Lovelesses. Now we can create the datum. As you remember, we can see right here. The datum swap contains the beneficiary and the price. And so we have to provide both the beneficiary and the price that we just hard-coded for this specific test. And then we want to know the inputs. As input, we're going to create the swap input. Remember that this is the input that is sitting in the swap contract and that it has all the correct values. We want to create the swap input contains the tokens that we're trying to sell. And then as output, we are going to create the beneficiary output, which is the output in the beneficiary's wallets. So we have to provide both the beneficiary and the price. And create the context with these inputs and outputs. And then we can, once we have our context, we have our datum, and our redeemer is void, we can run the exploitable swap datum, providing the correct datum and the correct context. Woo, I'm losing my voice. So let's see. Let's run this. I can be even more specific, actually, with the tests. And I can say, this is not needed anymore. Lesson 4, exploitable swap. And if I do like if I were importing, dear Lord, I can say honest TX succeeds. And we have a bunch of warnings importing. Yeah, but these warnings are super annoying. It passed, but these warnings are again. There you go. We are Let's run again. In this case, we're only running the test and we're checking and testing. Lesson 4, exploitable swap, and specifically the honest transaction succeeds. Not all of the tests of the smart contract, just that specific one. There you go. There you go. And now, if we run it, it succeeds. Awesome. So if we try to consume the UTXO in the swap contract, and then at the same time, in the same transaction, we pay the fair price to the beneficiary, it passes. The function, the test passes. So it's okay, it's good. The buyer got his tokens, and the seller got his money. So it worked as expected. Amazing. Now let's try to game. Let's try to game the smart contracts. So now let's say we want to try to run the smart contracts, but we want to pay to the beneficiary. We just want to like consume the day to swap, but we're not going to pay to the beneficiary. So we hard code as well the same beneficiary and price. We create the datum. We create the inputs. The input is again the same create swap input, but as outputs, now instead of creating an output for the actual beneficiary, we create a dummy output that it's pays something else to someone else, for not specifically for the beneficiary, and everything else is the same. So if we say pay nothing fails. I think, yes, I misspelled. Pay nothing TX fails. There you go. So if we don't pay to the beneficiary, we get that, as you can see, I just specify that this should fail. So it fails, and that's good. It should fail. And why did it fail? Well, because the value of loveless of the paid to the beneficiary is not bigger or equal to the price, because it's 0. So the price is 100. In 100 is not smaller than 0. So this is false, and the validator won't accept the transaction. It's going to fail. Make sense? Any questions? Okay. So this seems that it works, right? Should we just call it a day and go home and like send this?
You
Local
should
mode?
deploy it on mainnet and put some money in it. Then we'll see.
Exactly. So as the name of the validator might hint you, there's something that can be exploited in this validator, which maybe just it's not something you can think of quickly on the spot, but if you sit around and really try to like gain the validator, you can see that there is a way to get something that is not yours without paying. What happens? No, where is it? Here. So in this scenario, all good. We're fine. But what happens? Let's see. Let's just to simplify a bit. Price of the seller. And this goes away. There you go. So now, like we consume the smart contract, the swap, and we pay in a single UTXO everything that the seller wants. Seems like it makes sense, right? But the thing is, you can consume multiple inputs, including multiple swap contract inputs. So let's move this a bit. So we have enough space. So we can, not only this swap, this is huge, really. Let's say that the seller doesn't only want to sell like this set of NFT of tokens or NFT or whatever, but he wants to sell more stuff. So the seller could, like, you theoretically could like create a bunch of UTXOs in the swap contract containing different assets and asking for different prices and stuff like that. But if you happen to sell two assets, two UTXOs with the same price, there's an issue there. So let's copy this. Let's move it again. So I could have created this in the same transaction or for some other transaction. That's not really important. The important part is that I am consuming both in my transaction. The buyer is consuming both. And here, actually, the value doesn't matter. So I can just say, how was it? ABC tokens. And here we have some random NFT. So here's the thing. Validators will check for each UTXO, for each output that we want to consume, that UTXO can be spec'd. So let's see if I can use red. So first is going to go to the first one, and if the price is let's say that the price is 100, and here the price is 100. So I could put different prices, right? And that wouldn't be an issue. But I can also put the same price, and that can be an issue. It is an issue. So imagine that you're creating a bunch of UTXOs and someone wants to consume these ones. So the validator is going to, the swap contract is going to first say, okay, you are trying to consume this NFT. No problem. I'm going to check in your UTXOs if you are paying the price, which is 100. This is the price that I'm asking. So if you're paying me 100, all good. So this validator, this UTXO is being, can I do multiple? No, but I can do like this, I think. This UTXO, no, I cannot. Well, a straight line will be. So this validator can be, let's use an arrow. He's going to check, hey, are you paying me are you paying the seller 100 ADA? And it's going to check this UTXO and say, yes, you're paying this, you're good, you can consume me. And then in a different check, this validator is going to check for this specific UTXO, hey, are you paying 100? And it's going to see that, yes, I am paying 100. So it's going to say, okay, then I'm going to unlock. I'm going to allow you to consume my UTXO. So there's an issue here. You are the buyer is consuming two assets of 100 Lovelaces, valued 100 Lovelaces each, but it's only paying 100. It should be paying 200, but we're not checking that. We are just checking that each one checks that the buyer is paying the correct price for himself, for this specific UTXO, without taking into account other UTXOs. So that's an issue, because all of a sudden I can spend twice paying once. That's why this is an attack called double spending or double satisfaction. I'm satisfying two separate cases, two separate UTXOs with a single payment. This is really important to address, and it's something all UTXO-based blockchains suffer. But there are a bunch of solutions to this. What we want, actually, because we're running out of time, so I hope you understood the concept. What we want is to check if we can do that with the current validator. So for that, I'm going to create a new check that is called double spending transaction succeeds. But it shouldn't. So this one doesn't fail. As you can see, I haven't added the fail keyword. And it's the same as before, beneficiary, price, datum. But in this case, the inputs, I'm creating two separate swap inputs, like the 0 in the position 0, index 0, and index 1. So now, this transaction is consuming twice from the swap, but I'm creating only once one output paying the price to the beneficiary. So this is the double spending. I'm paying once, but consuming twice. And this should not succeed if in the ideal world, but it does succeed because our validator is not strong enough to protect us from that. So if we run this, if we run double spending DX succeeds, we see that it passes, but it shouldn't. No one should be able to attack like this a validator. So we have to patch this. That's it for the exploitable swap. So we have a working validator, but we found out by testing, we checked that this is a pretty common thing to make sure that doesn't happen. We checked that we run a test that shouldn't succeed and succeed, so that hints that there's something wrong with our validator and we need to fix it. So how to fix it? Maybe we run out of time, so so here we have the patch swap, but I'm not going to show you. But actually, I could just hint the solution to you. If I run let's run all the tests in exploitable swap. So that's like the whole overview of the test of exploitable swap. And then we have the patch swap, which has the solution to avoid this double spending attack. And if we run the same tests that I'm not going to show because you have to implement that yourself, if you run the same test for the patch swap, we see that here the double spending transaction should fail, and I indicated that should fail. And in this case, I checked that we are only consuming one swapped input. If we come here, now the swap contracts, when it's checking, not only checks that the seller is being paid, but it also checks if there are other outputs of the same contract. If there are other outputs, this will fail. So all of a sudden, you cannot consume multiple UTXOs in the same contract in a single transaction at the same time. So you have to do multiple transactions. You can consume one per transaction. And that's how we solve the problem. But there are other ways. Like we could say here we could add a unique ID, and we can use here as well a unique ID. And now the validator checks not only that the seller is being paid, but also that the unique ID is being, only the UTXO with this ID is being consumed right now. So we have to do some small modifications, but could be possible. And there are other ways, but like the most common is these ones, like these two. And the first one that I explained, that just making sure that there's no other UTXO being consumed, is the one that I implemented in the patch exploitable swap. That now is not exploitable anymore. So because we ran out of time, I'm going to give you as a homework. You already saw the test, so you can like follow the lecture to write them again, or just copy them or rewrite them again without looking, which would be great. And then once you check that the double spending transaction shouldn't succeed, like succeeds but it shouldn't, then you can modify the swap contract to make sure that this test doesn't pass anymore, that you cannot exploit the swap anymore. And that's the homework for this lesson. Like rewrite the tests, modify the swap so this last test doesn't pass anymore, and you're good to go. You can deploy to mainnet. Now, not really, but you are a huge step closer to deploying on mainnet. Any questions, comments?
I'm not sure we are out of time, but I mean, I personally don't like that solution to fix it, because I mean, as far as I'm concerned, one of the biggest advantages of this EUTXO model is that the composability of smart contracts, that you can basically combine inputs that belong to different smart contracts, even smart contracts that, I mean, at the time of writing, you're not aware that they exist. And so there's this solution that I prefer to solve this, and that makes use of a feature that maybe we haven't mentioned yet. I mean, when we talk about datums, I mean, we normally think of smart contracts. So normally we always use datum at the smart contract address, not at the pub key address. But Cardano allows datums everywhere at every output. So in particular, also at smart contract at PubKey outputs, like these payment outputs you do. And I mean, I always compare it with the real world. I mean, this is actually a problem that could also occur in the real world. I mean, let's say my example is obviously, let's say you are a bit sickly, so you often have to go to the doctor. So in 1 month or so, you go to your doctor twice, and he sends you 2 invoices. And by accident or by chance, they happen to be the same amount, like $100 twice. And now you transfer. I mean, you make a transaction, online banking, and send him $100 only once. And now think of his poor accountant. I mean, how must that person check whether all the bills were paid? And I mean, she would, I mean, she goes through the invoices. She sees, okay, here you were invoiced for $100, and then she checks and she sees there was an incoming payment from you over $100. So she makes a check mark to the invoice, and then like a couple of hours later, she comes to the second invoice, and again she sees that you paid $100. So I think that could even happen in real life if it was like that. So it's not intrinsic to blockchains. And I mean, the way doctors and like other businesses normally solve that is that you don't just pay the money, you are supposed to give some sort of reference as well. I mean, normally they have like an invoice reference ID or whatever. And then, I mean, on the invoice, it says invoice ID, whatever. And then you are supposed in your online banking transfer to not only send the money, but also mention that reference. And then it's easy for the accountant to match the payments against the actual invoices. And the exact same trick you can do here as well by using this datum feature. So, and as invoice reference, you can actually use the UTXO ref of the input you're consuming. So in your example, I mean, you use the same smart contract as input twice, but they are obviously different UTXO, so they have different UTXO refs. And then what I would do is in the payment outputs, I would attach a datum, and the datum is just the UTXO ref of the input I'm paying for. And then the validator would not just look for payment to the right address over the right amount, but also with the right datum. And then in your case, you would need 2 separate outputs with different datums for the 2 inputs. So I believe that is the best solution for this, because it still allows you to freely combine inputs. But it's just my opinion.
No, it's like it's the correct way actually, but more complicated.
Yeah, sure. And I mean, it's probably you get away. I mean, this is at least simple. And I just wanted to say that, I mean, there are ways where you can still have the feature that you have several at the same time. So you keep the throughput and the composability, but can still fix this double satisfaction problem.
Yes, and there should it's in working like more solutions. There's a CIP Cardano improvement proposal to add a tag to transactions, to UTXOs, to like try to do the same like unique ID thing, but without sacrificing the datum.
I see.
But it's not approved yet. It's like on draft.
Right.
But yeah, it's like as long as you understand what's the issue, and then you can figure out how to solve that in many different ways.
I just find it interesting. I mean, apart from this specific problem, what I just said about the doctor, and I mean, often you realize it's like, I mean, once you understand the problem, I mean, it as I said, it has nothing to do with blockchain. That's a general problem in our world. How do you associate payments with invoices? And I mean, there is already a solution that is frequently used. And I find it somehow interesting that you can basically let that solution inspire you to also solve it in the blockchain context. Just as a general tip how to think about these problems. Anyway.
Awesome. So yes, I think we managed to cover everything. We are a bit over time, but we also usually start a bit later until everyone connects. So I think we're fine. And yes, that's it for today. See you on Friday.
By the way, sorry. I think not. I mean, I assume. I mean, definitely in Germany, Friday and Monday are public holidays, and I believe it's also IOG company holidays.
Hmm.
And I would assume that's also holidays in Kenya.
Yes, yes, it is. It is Good Friday and Easter Monday.
Right. So probably
Yes.
the next lecture will only be on Wednesday then.
Okay.
Yeah, that April, yes.
Do you have to work, Robertino? No.
No. No, but I was going to either way. Okay, perfect. Okay, so see you everyone in a week then. Have a great rest of the week and weekend. And any questions, feel free to ask synchronously.
Thank you.
Bye.
Okay, see you everyone. Thank you.
Happy
See you.
Easter, everyone, and see you and talk to you next week.
Okay.
Thank you.
Bye.
Bye.